I'm going to go through here and kind of talk about kind of the big picture and the concepts, maybe from a 20,000 foot level in terms of what we're doing in terms of training and evaluation. And the objective we're kind of looking at is we want to use various sources of information to do a better job of predicting an animal's genetic merit. And if we take a look at what we have in terms of sources of information, we have phenotypic and pedigree information, and that's kind of the traditional source in terms of what we used in terms of predicting an animal's genetic merit. When you look at pedigree information, really what that was providing is kind of the average relationship between animals. What's becoming more and more common is we're seeing more and more genomic information coming in. And one way to take a look at it is it gives us a finer grain relationship in terms of how animals are interrelated to each other. And as we get better in terms of identifying which genetic markers to use and focus in, it's taking a look and say, this is the relationships that matter. Along that, we need to bring these sources of information together, figuring out in terms of how to go through and weight these various sources of information. And that's kind of where the statistical model part comes in. And we've seen lots of different types of statistical models, mixed models, Bayes A through Z, single step, two step, and there. But we looked at there was just kind of, here are the sources of information. Really, what's important is how much information we have. And we can kind of break it up into three things, kind of at a very basic level. The amount of information we're going to have is going to depend in terms of the number of animals we collect phenotypes on. So for some traits, that's fairly easy. We collect a lot. For some of the more novel traits, we collect less information in there. Whoa. And where's that thing? Also in terms of the numbers of animals genotyped. As we go through and we're increasing the number of animals genotyped, we're getting more information from that end. And then as we go through and increase the number of SNPs, we're getting more and more information there. And it'd be nice if it was all simple. We just have to count the numbers and say we're doing good or doing bad. But it's a little bit more complicated than that. It's not simply the number of animals phenotyped. Fundamentally, it's how strong is the relationship between the phenotype and the animal's genetic merit. And part of that is this a very heritable trait? Is this a lowly heritable trait? Are we collecting information on a correlated trait or not? But it's also how strong the relationship is between the animals we're phenotyping and the animals we wish to evaluate. Who are we wanting to make decisions on at this point? And this population of animals that we wish to evaluate changes over time. The number of animals genotypes is important, and we're seeing that we're collecting many more genotypes. But it's not just the absolute number. You don't just double and get twice as much information. It's, again, how strong the relationship is between the genotyped animals and those with phenotypic information. If those are unrelated, it's really not providing us any information at all. Okay? And also, how strong the relationship is between the genotyped animals and those we wish to evaluate. Okay? So we want, in terms of genotyping, from an information standpoint, we want to be genotyping animals in which they're strongly related to those with good phenotypic information, and we also want to go through and have them also close to the ones we want to evaluate, who happen to be the ones with the least amount of phenotypic information. Okay? And then the number of SNP, I kind of remember way back when was like 3. Then the hundreds, and then the tens of thousands, and the hundreds of thousands, and I guess we get the sequence information, and we'll have more stuff than we can know how to deal with in there. But part of it is, when we're taking a look at the SNPs, can we get them closer to the actual sources of genetic variation? We're collecting markers. We can go through and actually get the genes and the variants that are actually causing it. There's an opportunity there. And it's not just more is more. Okay? But a lot of that, in terms of going through, part of it is just noise. SNPs come in, they provide information, provide signal, but it's not just signal. It also comes along with noise. And we need to balance that off. In terms of the statistical model, okay, it's just a mathematical representation of the underlying biology. And I'm not the first one to notice this, but whenever I write up a statistical model, the one thing that I'm extremely confident of is it's wrong. Okay? Okay? First of all, regardless of what we do, biology is a lot more complicated than any sort of statistical model. I don't care how fancy you make it. Okay? Biological mechanisms are complex, and the more you deal with it, back when I was an undergrad, I took genetics, I thought, oh, this isn't too bad. And every time I took another course, I learned that I didn't really know what I knew in the other course. And there I felt like I knew a little less each time. Okay? And really, if we want to evaluate a model, it's really how good is it at actually making predictions. And not just making predictions, but predictions of things that we are interested in. So we take a look in comparing different models and different panels and different approaches. It's always getting back to how good did it actually do. Okay? Any model is going to depend on a large number of unknown parameters. So what the heritability of the trait? What are the genetic correlations between the things that we are measuring? If we have SNPs in there, what are all those SNP effects? If we got 10,000, I got 10,000 SNP effects. If I've got 100,000, I've got 100,000. And if I got 1,000,000, I've got 1,000,000 now. Okay? In there. And one thing to bear in mind from mathematical, statistical standpoint, I just love making complicated models. That's fun, kind of build things up. What I find, and what everyone finds quite often, is that a simpler model can, and often does, perform better than a complicated model. If we kind of go through and we make everything fancy, one of the things we do when we make things fancy is we add additional parameters and things that need to be estimated. Everything that needs to be estimated is buying something from the information we're bringing in there. So we want models that capture the important features without going chasing after the things that are unimportant. And it'd be much easier if we could figure out what the important things were before we built the model. Okay? Now, there are a variety of different statistical models that we can take a look at. We've got single step Bayes, we've got two-step, we've got Bayes and C. I'm going to focus in on just one, and in terms of a two-step statistical model, more for the fact that that's being used pretty commonly right now. And since it's a two-step model, it has two steps, 1 and 2. The first part is there's a model that, in terms of building the prediction equation. Okay? It takes as input SNP effects, SNPs, and EPD information, so that's where the phenotypic information is coming in, on a set of genotyped animals, and it runs it through all these complicated things and cool stuff, and basically what it does is it outputs a prediction equation. Might be a good prediction equation, might be a poor prediction equation. Okay? Once we have that, we need to, the two-step model, we need to blend or bring in, one way or another, the predictions from that equations with the phenotypic EPD information in there. And that takes as input the prediction equation from the first step, along with SNP and EPD information on the targeted animals. Okay? Some of these animals might be the same. Some of them may be different, especially as we go forward. The ones we're really interested in are the ones that are new in there. And what it does is it just outputs an EPD. Okay? And it's just an EPD which now includes genomic information. And so we're going to be interested, well, I went through and did this. Okay? Did I do a good job or not? Okay? So Got a model, got a process. What do we need? Well, I got a statistical model. I need the parameters so I can actually implement that model. Okay? I'm going to need to come up with a prediction equation, and for the most part, that's just the SNP effects. I take a look at this SNP. Does it have a large effect? Does it have a small effect? Does it not tell me anything? And then I need the parameters to blend that genomic information in with our phenotypic EPD information. And of the parameters, the one that we kind of focus in on is probably the most important, not the only one that we need, is the genetic correlation between the predicted genetic merit and the true genetic merit. In addition to that, that's what I need to actually run the model. But we also need to how well that model is doing in terms of predicting the genetic merit of an animal. Okay? It's not good enough to just get a prediction. We want to know, is it doing a good job or a poor job? And that gets us to training and evaluation. When we talk about training, what we're focused on there is building the prediction equation. You're going out deciding which animals should I include, whose phenotypic information who I should include, whose genotypic information. Do I go through and just use raw EPDs? Do I deregress them? Do I deregress them this way, or do I deregress them that way? Do I fit a big single-step model? Okay? But that whole training is just going through and coming up with the prediction equation. And the prediction equation says if I provide another set of genotypes, I plug them in, the equation churns around, and spits a number out at the other end. The evaluation step is that once we've done the training, we've got two things left to do. I need to estimate the parameters, since it's a two-step model, for blending. Okay? And also, if I'm looking at doing something different, doing something new, can't just assume that it's going to be better than what I had before. I want to know, first of all, is it? And second of all, how much? And so we want to take a look in terms of how well the model is working. Okay? And that kind of comes through as I've got all these different statistical models. I go through and I pick one. I take a look at how that works. I might take a look at a different model and ask the question, does this work better? Or I might have the newest fancy-dancy model with all the chrome trim, and I want to take a look. Okay, it's certainly shiny. They're charging me twice as much for it. Does it work better? Okay, well, it's shiny, so yeah. Okay. Okay. So I want to kind of back up because we're going to be doing training and evaluation. I'm going to have to decide who I'm going to be using for training and who I'm going to be using for evaluation. And so I can categorize my animals into three kind of categories that are interesting. Okay? First of all, I have these higher accuracy animals that have been genotyped. And when we first went out and started collecting genotypes, these are the ones we went after. Quite a few of those. So I have those higher accuracy animals. We also collect information, because there's only so many of those, on lower accuracy animals that have been genotyped. And the final category, which is the one that for the animals we're actually interested in, these are low accuracy animals that haven't been genotyped yet, but I'm planning on going on and doing it. What do these provide? Okay? So for the higher accuracy animals that have been genotyped, they're very valuable. They provide the most information for building my prediction equation. Okay? Might not be, if they're too far separated, they might be providing a lot of information, but not the information I want, but that's a separate story. So they're providing the most information. So I'm in the training step. I want animals like this. If I take a look in terms of going through and seeing what they benefit in terms of a direct benefit from having them, okay? Got this high accuracy animal. It's really great, building great prediction equations. What additional benefit do I see in the genetic evaluation of that animal? This has been said several times by several people. They see little, if any, direct benefit from having that additional genomic information. So much of the information's already come in on the phenotypic side. Adding the genomic information in terms of improving the accuracy of that animal's EPD is minimal. Now what it does do is, if you're going through and you say, well, why should I bother? These models are being trained on the genetics that we're feeding in. The prediction equations would be expected to work the best on the genetics that are being fed in there. So you want your genetics in there so it does well on your animals. Okay? Next we have the lower accuracy animals that have been genotyped. On a one-per-one basis, they don't provide as much information, okay, in terms of building an equation, but they do benefit some from the additional genomic information. So we're taking a look at those. Whether these actually get genomically enhanced, maybe not so much a big deal. Here there's some benefit directly to the animal in there, so they have a greater benefit in there. And last, we have those low accuracy animals that have been genotyped. So if we take a look in terms of raw numbers, in terms of animals that are getting genotyped now, this is the biggest class in there. We're getting the animals coming in. They have very little, if any, of their own phenotypic information. Basically, they have mid-parent average in there. And they're really providing no information. They make the number of animals genotyped larger. But in terms of building a better prediction equation, they really don't help us. But the ones that are not doing the work get the biggest benefit. Okay? The most from the addition of genotyped information. So I can't say, well, I just want to build a wonderful prediction equation. I'll just genotype high accuracy animals. Because that's not telling you information about the ones that you actually want to make selection decisions on. And that, just like life, the ones that do the work get the least benefit. Okay? Okay, so now we have to go through and form training and evaluation. Training we have going out there because we want to build a prediction equation. Evaluation, we want to see how well it's working. Okay? Well, one thing, I can just say everybody's training. I'm just going to put everybody in, use them for evaluation too. Okay? So if I take a look at the prediction equation, it does a pretty good job. It's probably about the best prediction equation I'm going to get out, and it has a purpose in there. But what we observe is that it does a really great job of reproducing EPDs of the currently genotyped animals. So one way I know that if I messed up, if I go through and things are looking really, really, really good, I start wondering if I have training and evaluation overlapping each other. I'd like to say that I've never done that. I have done that, and I said, wow, this is amazing. And it just looks great. And that's usually when I say when things are looking really, really good, that I screwed up somehow, which is usually the case. When I do a little better, I say, okay, maybe I'm good. But if I do a lot better, I say, okay, what did I do wrong? Okay? And really it's getting back, and you're familiar with this, we've got lots of individuals that are really great of predicting what happened last week. Okay? You go on Monday, everybody can tell you, make really good predictions about how the football teams did on Sunday. Or if they played on Saturday, they tell you on Sunday, and they can tell you why. And the predictions are very accurate in there. And they can get the other set of experts who can tell you why the economy is the way it is and can explain everything in there. But you bear in mind is that just because you're good at predicting what happened last week doesn't mean that you're any good at predicting what will happen next week. So going back and taking a look, it's okay, I can do a really great job using last week's information and predicting last week. Okay? That doesn't tell me squat about how I'm going to do next week. Okay? And there. Now we do train on all the animals, but the prediction equation we get out is really appropriate for those animals that haven't been genotyped yet, who are outside of the animals used for that training. Which says, well, if I'm going to do training and evaluation with a current set of animals, I can't put them all in training and all in evaluation. I need to put some animals in training, and I need to hold some animals back. Okay? That's kind of frustrating in there. And so how do we work with that and try and make maximal use of the information? And we use something where you've probably heard in terms of we've done k-fold cross validation. I guess I've got a symbol there, so that might look like kind of an equation. Okay? So what's k-fold cross validation? What I do is I take the animals and I partition them up into several different groups. 3 groups, 5 groups. That's the K part. Okay? So every animal is in one group, one subsample or another. And then I go through and I create folds of the data. And that sounds, whoa, that's fancy. It's not that fancy. Okay? So I take each subsample and I create a training set and evaluation set, my fold. The evaluation set are those animals in the subsample. To evaluate those animals, I use all the individuals who weren't in that subsample. Okay? So when you see 3-fold cross-validation, if I take a look at fold 1, to evaluate the animals in subsample 1, I'm using all the information from the other 2 subsamples. And then I say, well, why can't I do the same thing for the animals in 2 and in 3? Now I can go through and I can use all my animals in evaluation and evaluate them using animals without having those animals in that same in there. So it's nice and we can do everybody. Okay? And what we get out of there is we obtain estimates of the parameters needed for blending. You really don't get that out of kind of you train on everybody. Because we can take a look in terms of, well, if I'm going to predict this one, how well am I actually doing? And equally important, we get a measure in terms of, as opposed to how good am I predicting last week, how good am I predicting this week from the other week's information? Okay? So in terms of the incorporation of genomic information, kind of to bring that back, for the genotyped animals subsample 1, we use the prediction equation trained on 2 and 3. For 2, so if I'm going to go through and I want to incorporate that in terms of getting EPD enhanced for genomic information or including genomic information, if the animal happened to be in subsample 1, I'm going to use the prediction equation based on the other 2 folds, 2 subsamples. Same thing for animal 2, 3. So that allows us in a fair way for the animals used to training to actually go through and have them benefit from there without using their own information. We really don't need something that's going to just tell us that the animal's EPD is what we had before. And then for animals not used in training, we use a prediction equation trained on subsamples, the whole set. Okay? And then for the blending parameters, okay, we're going to use for all the animals, we're going to use the one by taking estimates of those blending parameters here, here, and here, and in essence kind of average them together. It's a little bit more complicated than that, but that's basically what happens. So I go through a lot of fancy math here, and I get a number that's pretty close to the average of the other ones. Okay? And to kind of tie that up, okay, time marches on. Okay, we got training, we got evaluation. So we're like, okay, I did it, I'm done. In there, but as we go through, as we go forward, additional animals are getting genotyped. Okay, in there. Some of the animals that were lower accuracy before that had genotypes are now higher accuracy animals. Okay, we're getting additional phenotypic information as we're going through. That's why some of the low accuracy animals are moving up to being higher accuracy. New genotyping platforms are coming online. It's probably not all that far off. when we'll be actually dealing with incorporating sequence information directly into improving our genetic evaluations. Also going through, we've got our lovely molecular geneticists. Okay, I show them equations and they go, yuck. And then they show me their labs and I say, oh shiny, I have no idea what that's doing in there. But one thing, as they're going through, they're narrowing in terms of what the different actual functional variants that are affecting the traits. That information is going to be coming in. We want to make use of our colleagues' information. Okay, and the animals we wish to target are changing. Okay, as we go forward, we're starting to want to target animals that didn't exist 2 years ago. Those are the ones we're interested in. And it's for these reasons and others that training evaluation needs to be done on a regular basis. It's not something you can be done and do with. Some of the questions change. And there, we change models and what we do in each part of training and evaluation changes. But this process is something that's ongoing. Okay, and with that, I'll open up to questions. Okay, so in terms of evaluating the equation, what we do is I get a prediction out of kind of the model. So it comes out, I feed the SNPs in for an animal, I get a prediction kind of that animal's genetic merit just based on the marker information. Then I go through and I take a look at, from the phenotype side, I got an estimate in terms of what the actual genetic merit of that animal is. And I take a look how strongly they are associated in there. So if it does a good job of predicting the EPD of an animal that it hasn't seen in training, I say that's pretty good. I need to do some fancier stuff to take into account that if I go through and say, how well is it predicting a high accuracy EPD? Okay, that's actually telling me more information. If I get somebody who I have very little information on, I have to take into account that there's a lot of noise in there. Well, I kind of look at it from a practical standpoint. Yeah, so I mean, from a practical standpoint, you're kind of going through and it's saying, well, how often things are changing, and I'm almost thinking, if I was to say how often, it's almost like kind of an annual or semi-annual. You're kind of taking a look at, we're at that same point where years ago when we ran SIRE evaluations, I think we started out, we ran them a year, and then as the technology got better, it moved up to 6 months as the computational resources. I'm kind of taking a look here. I think where we're at now is, my feeling is it's kind of like that annual basis. As we go through and the pipelines get better, we're moving to semi-annual, and at a certain point it becomes a continuous process. My guess is once you move kind of past the kind of that semi-annual, there's probably not a whole lot of benefit. But this is just me speaking out the top of my head. Somebody might show that there's a huge benefit for doing it more often.
It's probably related to the proportion of new animals coming in that are genotyped. For some breeds that have been really relatively static, it may be less important. And I agree it'd be nice to have continual retraining, recalibration, but as we know, that process isn't quite as seamless as we might like it to be. So
we get closer.
Yeah, that's
we
right.
get closer.
That's right. Other questions for Steve? I'll maybe ask just one quick one, Steve. You mentioned deregression, and perhaps that's not a concept familiar to everyone.
Oh,
so
okay.
if you just kind of quickly tell the group what you mean by deregression.
Okay, so what deregression is we take a look at an EPD, and we take a look at an animal's genetic merit. You can view the EPD as being a function of the animal's true genetic merit, the signal, plus the noise. Because these things are regressed towards the mean when we have less information, deregression goes through and inflates the EPD so that the amount of genetic variability is the same, and then we're kind of taking into account as the residual variability. We could do all this without deregressing. We could work with the raw EPDs, but as opposed to saying that genetic variance is the same, we'd say the genetic variance is changing. And there, if we do deregressed, we say the genetic variance is the same, but the noise component changes quite a bit.